In the summer of 1989, a spacecraft that had already been flying for 12 years arrived at a planet no human instrument had ever properly seen before, and what it found there included a storm the size of Earth, a moon spewing ice volcanoes into the near absolute zero cold of deep space, and a wind speed faster than anything ever recorded anywhere else in the solar system. That spacecraft was Voyager 2, and Neptune wasn't even its final stop. It was simply the last planet on a journey that had already rewritten what we knew about 4 different worlds, and it was about to keep going 40 more years, all the way to the edge of everything the sun's influence can reach. This is the actual story of what Voyager 2 saw, planet by planet, moon by moon, all the way out into interstellar space, using nothing but real, documented mission history, drawn directly from NASA's own records of one of the most productive single spacecraft missions humanity has ever launched. Voyager 2 launched on August 20th, 1977 from Cape Canaveral, Florida, 16 days before its twin, Voyager 1. That launch order matters, because despite leaving Earth first, Voyager 2 was placed on a slower, more roundabout trajectory, one specifically engineered to take advantage of a rare alignment of the outer planets that happens only once every 175 years. That alignment meant a single spacecraft could use the gravity of each giant planet it passed to bend and accelerate its path toward the next one, a technique called a gravity assist, saving enormous amounts of fuel it never could have carried otherwise. It was this specific trajectory, and only this trajectory, that made Voyager 2 the only spacecraft in human history to visit all 4 of the solar system's giant planets in a single continuous mission. To put the ambition of that plan in perspective, the same window of planetary alignment that made this grand tour possible wouldn't occur again until the 22nd century, meaning NASA's engineers in the 1970s were working with a launch opportunity that, if missed, would not have returned in any of their lifetimes, or likely in the lifetimes of anyone reading about the mission today. Its first stop was Jupiter in the summer of 1979. Voyager 1 had already flown past a few months earlier, so Voyager 2's job was partly to fill in what its twin had missed, using a different flight path that let it examine the giant planet system from new angles. It captured its closest approach on July 9th, passing within about 350,000 miles of Jupiter's cloud tops. What it found reshaped how scientists understood the entire Jovian system. The Great Red Spot, that massive, centuries-old storm larger than Earth itself, was revealed as an extraordinarily complex, swirling structure, rotating counterclockwise with smaller storms and eddies threading through the surrounding banded clouds like currents in a vast, endless ocean of gas. Scientists had studied the Great Red Spot from Earth-based telescopes for well over a century by that point, but nobody had ever been able to resolve the fine detail of its internal structure, the way individual bands of cloud curled and interacted at its edges, until Voyager 2's cameras finally captured it up close. Voyager 2 also conducted something engineers called a 10-hour volcano watch, aimed at Jupiter's moon Io, confirming what Voyager 1 had first spotted months earlier. Active volcanic eruptions, the first ever discovered anywhere in the solar system beyond Earth. Between the 2 Voyager flybys, scientists documented 9 separate volcanic eruptions on Io, and evidence suggests several more happened in the months between the 2 spacecrafts' visits, meaning Io's surface was found to be changing dramatically in real time, something nobody had any reason to expect from a small, seemingly unremarkable moon. Astronomer Linda Morabito, working with Voyager 1's imaging data, had first spotted a strange plume rising from Io's surface just months before Voyager 2 arrived. And Voyager 2's dedicated observation window gave scientists their first real opportunity to study that ongoing volcanic activity in sustained detail, rather than as a single, brief glimpse. Voyager 2 also photographed Europa in detail for the first time, revealing a strange, cracked, almost featureless icy surface covered in intersecting linear fractures, an image that would eventually help convince scientists that a liquid ocean might be hiding beneath that ice, a hypothesis still being actively investigated by missions today, including NASA's Europa Clipper spacecraft, currently en route to that very moon. From Jupiter, Voyager 2 coasted onward to Saturn, arriving in August of 1981, roughly 2 years after its twin had passed through the same system. It photographed Saturn's rings in extraordinary detail, revealing structures within structures, thousands of individual ringlets rather than the handful of broad bands visible from Earth-based telescopes, along with strange temporary features scientists nicknamed spokes, dark radial markings that seemed to form and dissolve across the rings in ways that puzzled researchers for years afterward. To this day, the precise mechanism behind those spokes, believed to involve fine electrically charged dust particles temporarily lofted above the ring plane by Saturn's magnetic field, remains an area of active study, a genuine open question first raised by Voyager 2's cameras more than 4 decades ago. It studied Saturn's moon Titan, confirming a thick, hazy, nitrogen-rich atmosphere so dense that Voyager 2's cameras couldn't actually see through it to the surface below, a mystery that wouldn't be solved until the Cassini mission and its Huygens probe finally landed there more than 2 decades later, revealing rivers and lakes of liquid methane hidden beneath that opaque orange haze the whole time. During this flyby, mission planners made a deliberate decision that would define the rest of Voyager 2's journey. Rather than using Saturn's gravity to angle toward Interstellar space immediately, the way Voyager 1 eventually would, they aimed Voyager 2 toward a very specific, narrow trajectory window that would carry it onward to Uranus, and if that worked, potentially all the way to Neptune after that. It was a gamble on a spacecraft that had already outlived its original mission planning, betting that hardware built in the mid-1970s could keep functioning reliably for another 8 years of continuous deep space travel through temperatures and radiation environments far harsher than anything encountered at Jupiter or Saturn. Nobody involved in that decision could have been entirely certain the aging spacecraft systems would survive the journey, and yet every single instrument needed for the encounters ahead continued operating exactly as intended. That gamble paid off. On January 24th, 1986, Voyager 2 became the first, and to this day, the only spacecraft ever to fly past Uranus, coming within about 81,000 kilometers of the planet's cloud tops. What it found was strange, even by the standards of a mission that had already rewritten planetary science twice over. Uranus is tipped over on its side, rotating at an axial tilt of nearly 98 degrees, essentially rolling around the sun rather than spinning upright the way most planets do, and Voyager 2's instruments captured this bizarre orientation in direct physical detail for the first time. Scientists still don't fully agree on what could have knocked an entire planet onto its side so dramatically, though the leading theory involves a massive collision early in the solar system's history, a mystery Voyager 2's data helped establish but never fully resolved. Its magnetic field turned out to be just as strange, tilted a startling 59 degrees away from the planet's rotational axis and offset from the planet's actual center, trailing a corkscrew-shaped magnetic tail stretching some 10 million kilometers behind it into space, twisted into a helix by the planet's unusual spin. Voyager 2 discovered 11 entirely new moons during this single encounter, along with 2 previously unknown rings, expanding humanity's catalog of the Uranian system dramatically in the span of just a few hours. The spacecraft also measured the length of a single Uranian day precisely for the first time, clocking it at 17 hours and 14 minutes, a number that simply didn't exist anywhere in human knowledge before that flyby. Much of Uranus's visible cloud structure remained obscured beneath a thick, uniform haze, but false color and contrast-enhanced images did manage to reveal faint bands of concentric clouds circling the planet's south pole, hints of weather patterns still not fully understood even decades later. 3 years after Uranus, on August 25, 1989, Voyager 2 reached Neptune, becoming, once again, the only spacecraft in history to ever visit this particular world. It was the final planetary encounter of Voyager 2's primary mission, and NASA's engineers and scientists treated it accordingly, gathering as much data as they possibly could during the brief window available. What they found was a planet far more dynamic and violent than anyone had predicted for a world sitting so far from the sun's warmth. Voyager 2 discovered a massive, dark, rotating storm system in Neptune's atmosphere that scientists nicknamed the Great Dark Spot, roughly comparable in scale to Jupiter's famous Great Red Spot, swirling in a planet that receives less than 1,000th of the sunlight Earth does. Wind speeds recorded in Neptune's atmosphere reached upward of 1,300 miles an hour, the fastest winds ever measured, anywhere in the solar system, an almost incomprehensible figure for a planet so cold and so distant from any obvious source of that kind of atmospheric energy. Voyager 2 also confirmed that Neptune, like Jupiter, Saturn, and Uranus before it, has its own faint system of rings, settling a question astronomers had debated based on ambiguous ground-based observations for years. And then there was Triton, Neptune's largest moon, which turned out to be one of the strangest, most unexpected discoveries of the entire mission. Voyager 2's images revealed active geysers erupting directly from Triton's icy surface, plumes of nitrogen gas and dark dust shooting miles into the moon's thin atmosphere, making Triton only the third body in the solar system after Earth and Io, confirmed to have active geological venting happening on its surface in real time. Triton's surface temperature was measured at roughly 38 Kelvin, making it one of the coldest measured surfaces anywhere in the solar system, and its unusual backward orbit around Neptune, moving in the opposite direction of the planet's own rotation, strongly suggested it wasn't born alongside Neptune at all, but was instead a captured object, likely a dwarf planet very similar to Pluto, pulled permanently into Neptune's orbit sometime in the ancient past. With Neptune behind it, Voyager 2's primary planetary mission was complete, having visited all 4 giant planets using a single spacecraft, a feat that remains unmatched by any mission before or since. But the spacecraft itself kept going. Its trajectory, shaped entirely by the cumulative gravity assists it picked up at Jupiter, Saturn, Uranus, and Neptune, sent it arcing downward, out of the flat plane in which all the planets orbit, and onward into the vast, largely empty region beyond. For the next several decades, Voyager 2 continued transmitting data about the outer reaches of the Sun's influence, measuring the solar wind as it gradually thinned, tracking cosmic ray levels as they slowly climbed the farther the spacecraft traveled from the protective bubble surrounding our solar system. That protective bubble is called the Heliosphere, and its outer boundary, the heliopause, is the actual physical edge of the solar system, the point where the constant outward push of the solar wind finally loses its fight against the pressure of the interstellars, medium pressing in from outside. On November 5th, 2018, Voyager 2 crossed that boundary, becoming only the second human-made object in history to leave the solar system entirely, following its twin, Voyager 1, which had made the same crossing 6 years earlier, in 2012. Voyager 2 made this crossing at a distance of about 11 billion miles from the Sun, moving at roughly 34,000 miles an hour, and because Voyager 2's plasma science instrument was still functioning at the time of its crossing, unlike Voyager 1's equivalent instrument, which had already failed years before its own heliopause crossing, Voyager 2 was actually able to provide scientists with direct, real-time measurements of the transition itself, giving researchers their clearest picture yet of exactly what the boundary looks like from the inside. What Voyager 2 found out there matched some predictions and defied others entirely. As expected, the density of charged particles jumped sharply as the spacecraft crossed into interstellar space, confirming that it had genuinely left the solar wind behind and entered a fundamentally different physical environment. But the data also revealed unexpected structure and complexity in that transition zone, plasma behavior that didn't match the smooth, gradual models scientists had built beforehand. Where researchers had expected a relatively simple layered boundary, Voyager 2's instruments recorded a more turbulent, more textured transition, adding to a growing body of evidence, also gathered independently by Voyager 1, that the edge of our solar system is a far more dynamic and complicated place than anyone had modeled before either spacecraft actually got there. Since that crossing, Voyager 2 has continued its journey deeper into true interstellar space, now sitting more than 13 billion miles from Earth, carrying instruments that continue to measure the plasma, magnetic fields, and cosmic rays of a region no other spacecraft has ever directly sampled. It remains powered by the same 3 radioisotope thermoelectric generators it launched with in 1977, generators whose output has been steadily declining for nearly 5 decades as the plutonium inside them gradually decays. That decline has already forced engineers to permanently shut down several of Voyager 2's original 10 scientific instruments, difficult decisions made carefully, years in advance, in order to stretch the spacecraft's remaining power as far into the future as physically possible. But even now, with only a handful of instruments still active, Voyager 2 continues doing exactly what it has done since 1977, sending back real, direct measurements from places no other human-made object has ever been. So here's what I actually want you to take away from this. Voyager 2's real journey out of the solar system wasn't a single dramatic moment. It was a nearly 12-year tour through 4 entirely different planetary systems, each one stranger and more unexpected than the last, followed by an additional 3 decades of quiet, patient travel through the darkening edge of the Sun's influence, and finally, a crossing into a region of space that had never once been directly sampled by any human instrument in the entire history of our species. Active volcanoes on a moon of Jupiter. A magnetic field twisted into a corkscrew at Uranus. Ice geysers erupting on a captured moon of Neptune. The fastest winds ever recorded anywhere in the solar system. And beyond all of that, a boundary at the edge of everything we call home, crossed for only the second time in human history by a machine built with less computing power than a modern calculator. Still working, still listening, still telling us what it finds. It's worth remembering, too, that every one of these discoveries came from a single, uninterrupted mission, using one spacecraft, one set of cameras, one set of instruments, carried across 4 planetary systems that no other single mission has ever managed to visit before or since. Every future mission to Uranus or Neptune, whenever it eventually launches, will be building directly on a foundation Voyager 2 laid down in the space of a few brief days at each world, decades ago, using technology that predates the personal computer entirely. That's the real scale of what this spacecraft actually accomplished, and it's still, quietly, adding to that legacy every single day it continues to transmit. If you want to know what Voyager 2 is still discovering out there right now, in real time, subscribe and turn on notifications. Because this nearly 50-year-old mission is still sending back genuinely new science today. And drop a comment telling me which of these discoveries surprised you the most. Because after everything this single spacecraft has already shown us, I think it's fair to say we're still only beginning to understand what it actually found.